So now we're going to talk about the actual mean value theorem. And this theorem is similar to Rolle's, but it has one less condition and the conclusion is just a little bit different. So now we're talking about a function f that has two conditions instead of three. So it's continuous on the closed interval and differentiable on the open interval. So we've lost that condition that the two endpoints have to be equal to each other. And now the conclusion is there is a number within that interval, but this time the derivative isn't zero. The derivative is, what is that? F of b minus f of a over b minus a. That looks distinctly like the slope of something. In fact, I think that this would be the slope of the secant line through these 2 points. So what the mean value theorem really says is not that there is a point, or the conclusion, I guess I should say, is this. There's a point on the interval where the slope of the tangent line, which is, of course, the derivative that we just talked about, f prime of c, is equal to the slope of the secant line. And the secant line is the line through the two endpoints of the interval, the f of b minus f of a over b minus a. So this is the slope of the tangent line. This is the slope of the secant line. And look, they're equal to each other. Okay. And we're going to actually present this geometrically here. Let's see if I can, once again, give us a couple quick pictures. I'm going to try to draw the same function, similar to that quadratic that we had before. Oops. That one went down a little steeper than I had hoped. Okay. And then we're going to find an A and a B. A and a B. And then have roughly that same A and B over here. This is our function f of x. So the first box that says, what is f prime of c interpreted to be geometrically? Well, if we add a c in, let's see here. I'm going to put my c right about here. Remember, f prime of c, okay, is in fact the slope of the tangent line. At x equals c. And in the next picture, f of b minus f of a over b minus a, that's a pretty straight line I just drew there. Is the slope of the secant line. And that's the secant line through f of a and f of b. Okay. So that's what those two things individually stand for. And if they are equal to each other, my final, see if I can actually get my line thing to work. It'd be nice if it was maybe not quite so wide. Okay. Nope. So I'm going to draw my function. I'm going to have my A and my B and the secant line that goes through those 2 points. And then I'm going to have my C, and what I want to do is get my tangent line to be parallel. So that's cool, I can rotate it. That's not actually what I wanted to do. I'm going to try it one more time. It's close. We're going to go with it. So if I have that point of tangency here, we're looking at the place where the tangent line is parallel to the secant line. That's sort of the geometric interpretation. Another way to say that is that the instantaneous rate of change at the moment of C is equal to the average rate of change over the entire interval. Because we can also interpret those slopes as rates of change. So it is a pretty powerful conclusion. It's just not one we use directly in a lot of problems. It's one that we tend to use to prove other things. So there are problems similar to the last one we did for Rolle's theorem that say things like verify that this satisfies the conditions and then find all the numbers that satisfy it. It's kind of a made up math problem. Like, you don't really ever have to do this for anything else. It's just kind of an exercise in proving that you know what the mean value theorem says. So you could certainly do those problems. I'm going to look at, there's one on the next page too, which is a similar type of application problem. But before we talk about those, I want to go to the places where the mean value theorem really actually gives us something that we are interested in. And that would be things like this first theorem. If f prime of x equals 0 for all x in some interval a to b, then f is constant on that interval from a to b. We drew this conclusion already, but we didn't actually prove it beyond just saying, yeah, well, that makes sense, because if it's 0, then it's like you're taking the derivative of a constant. It's just a number. And so if it's equal to 0 for all of those, then all of those x values, it's always going to be equal to that number, but it wasn't really much of a proof. So here is how we can actually prove this. So we're going to take an interval and we're going to just talk about two numbers, x1 and x2, that are sandwiched in between the a and the b on this interval. Okay. And then we're going to assert our mean value theorem on x1 and x2. There must be a c, number c, where f prime of c equals f of x2 minus f of x1 over x2 minus x1. Okay. But keep in mind that the first thing that this problem told us is that f prime of x equals 0 for all x's in this interval. So that means that f prime of c must also equal 0. No, don't do that. Get rid of that. Sorry about that. So this must also equal 0. Well, that only is true if the numerator equals 0. And if you simply add the f of x1 to the other side, we get this conclusion that f of x2 is equal to f of x1. But we chose x2 and x1 arbitrarily. We just said there are any values in between a and b. So we just proved that for any two values between a and b, f of x must equal f of x for those values. So therefore, f is constant on a to b. So it's a little bit more of a technical proof than we would expect that you would be producing in this class, but hopefully you're able to follow it. And it really gives us a much more concrete proof that, in fact, when a derivative is equal to 0 over an interval, the function is constant. And same thing goes for this next theorem. If f prime of x equals g prime of x for all x in an interval, then f minus g is constant. So in other words, that the f function is just the g of x function plus some constant. So again, this is something that I think we've talked about already, but to prove it, we're going to take the capital F function to be the f of x function minus the g of x function. And so then if we take the derivative of that, we get f prime of x minus g prime of x. And that equals 0 because what was the first thing we assumed in this problem? That f prime of x equals g prime of x. Okay. So we just proved that the derivative of this capital F of x is equal to 0 on this interval. But then by the theorem we just proved above, f of x equals c. It's a constant function. And so therefore, f of x, capital F of x, which is f of x minus g of x, equals c, leading us to little f of x is g of x plus c. So we basically used that same theorem we just proved to show yet another thing, that if you have two functions that have the same derivative, they are basically the same function, they just differ at most by a constant. So these are the kinds of things we really want the mean value theorem for. It's these theorems that tell us important things that we are going to use, but less of important things that we do with the mean value theorem is answer these sort of made up questions, like verify that this function satisfies the conditions and find all the numbers. I mean, we can do it, but it's really not something that provides us with a whole lot of value, which is the main reason why this lesson is really just a video lesson, making sure you know what the mean value theorem says, that you can see its use to us in improving theorems and coming to conclusions. And that's about it. We're not going to have practice problems like this example because they're just exercises that don't really give you anywhere in your understanding of the mean value theorem. So I'll include those solutions to these two problems in the completed notes that I post, but I'll leave them for you to go through on your own as you desire.